Well, good afternoon. Thank you for coming. We're going to talk, you're going to get a lot today about our next mission to the moon, the Lunar Atmosphere and Dust Environment Explorer. Now that's actually a fairly provocative name for a mission. I know I grew up going to school learning that the moon does not have an atmosphere. Well, the moon does have an atmosphere. It is admittedly very thin. If you were to take a cubic centimeter of atmosphere here at the sea level of Earth's surface, your sample would contain about 10 to the 19th molecules. If you were to do the same on the moon, your sample would contain about 100,000 to a few million molecules. Now that still sounds like a lot, but that's actually a very hard vacuum. It's on the order of what our astronauts encounter in the outermost fringes of the Earth's atmosphere when they do a spacewalk at the International Space Station. As thin as the moon's atmosphere is, though, it's not inconsequential. It actually glows. Now, you may have never noticed the bright glow of the lunar atmosphere, but that's because it's always right next to the big, bright moon. And if somehow you could remove the moon and leave its atmosphere behind, then with your unaided eye from a dark location, you'd be able to look up and see the glow of the lunar atmosphere. But its structure and composition are still very mysterious to us. Technically, the moon's atmosphere is classified as a surface boundary exosphere. And this is kind of a mechanical distinction. Here on the surface of the Earth, the motions of molecules are dominated by collisions amongst themselves. Whereas on the moon, it's rarefied enough that the molecules are clear to carry out nice ballistic paths, determined strictly by the moon's gravity and the amount of energy that they have. It's essentially a collisionless environment. We think there may also be an active dust component to the lunar environment. We got our first real hints of this back during the Surveyor landers, robotic probes before Apollo. And at times, as they would be sitting on the ground and they'd look toward the horizon, with the sun just below the horizon, they'd see these strange glows. Now, if the lunar sky was empty, you wouldn't expect to see that. There's nothing for the sunlight to be reflecting off of. But there it was. And so the thought was perhaps this was dust somehow levitated above the surface, catching the sunlight and reflecting it to the cameras. We got further support for this idea from the Apollo missions. And on several occasions, astronauts looking out the window of the command module while in orbit around the moon, again with the sun just below the horizon, would see these jets and streamers arching high up into the sky. What are they? Well, that's still really a mystery, but the thought is that, again, this could be electrostatically levitated dust, raised high into the sky of the moon, perhaps even up to the level that they were orbiting. How high would that be? So we're talking about tens of kilometers. Possibly. But it's a big question. And it's interesting to note that this was not always seen. This was not seen on all missions. So it's kind of a mysterious phenomenon. It's an open question from Apollo. We did get some support from one of the instruments left behind on Apollo 17 that was designed to look for micrometeoroid impacts. And one of the things it seemed to show was that twice every lunar day, there'd be very, very steep peaks of many impacts that are very, very, very small in size. And those peaks occurred right at lunar sunrise and right at lunar sunset. And so the idea of having this differently charged environment between the daytime side and the nighttime side, and having electrostatically transported dust going across that terminator, gained some support here. But it's far from a resolved issue. This is something that has been a topic of discussion ever since Apollo, and we're still trying to figure this out. So the lunar environment is actually a remarkably dynamic place. You have the sunward side charged positively to tens of volts. you have the nighttime side charged negatively to thousands of volts. And my colleague Diane Wooden will talk more about that for you this afternoon. You have a number of sources, or potential sources for the lunar exosphere. You have high energy photons, you have particles, you have the solar wind, you have meteoroid impacts, you have outgassing from the interior of the moon. It's a very dynamic place. Why do we care? Well, it turns out that this type of atmosphere that the moon has, this surface boundary exosphere, is an example of what is probably the most common type of atmosphere in our solar system. Mercury has one, our moon has one, many of the asteroids, many of the moons of the giant planets, even some of the distant Kuiper Belt objects, icy worlds beyond Neptune. The most common type of atmosphere in our solar system, and we know very little about it. But we happen to have one in our own backyard. How fortunate is that? So what we learned from the moon could be directly applicable to some of these other bodies we are so interested in studying. Asteroids, moons like Enceladus in Europa that may have water deposits, but are essentially airless worlds. So we're going to study this example of an exosphere with a new mission called Laddie, the Lunar Atmosphere and Dust Environment Explorer. It's going to go into orbit around the moon, and its goal is to study the composition and structure of the lunar atmosphere and look at the distribution, size, and charge of any dust that may be wafted into the lunar sky. It's going to go into orbit around the moon, retrograde, equatorial orbit, and then it will drop down low enough to actually fly through the atmosphere. We have 3 scientific instruments on board. You'll be hearing more about them today. But briefly, we have a mass spectrometer and an ultraviolet spectrometer to kind of sniff out what it is we're flying through. We also have a pyrolytic dust detector that will scoop up the dust and let us know how much there is, how big it is, what the charge on it is. We also have a technology demonstration, the Lunar Laser Communications Demo. To date, our planetary efforts have had space probes with transmitters that are broadcasting data via radio waves. As you get to great distances, obviously your bandwidth gets very low. We're going to try something new here, communicating over an infrared laser beam going from the moon to the Earth. They could potentially bring bandwidths of up to 622 megabits per second, broadband from the moon. So this is the design, this is the configuration of the Laddie spacecraft. It's not a big spacecraft. It's about 2 meters tall, about like me. 330 kilograms, again, about like me. 53 kilograms of payload mass. We like to say it's big science with a small spacecraft. So this is Laddie in the process of being integrated here at NASA Ames. This was happening in Building 240, which I believe you are going to be seeing today. So you'll see where this actually happened. Laddie is no longer there. It is now, Laddie has left the building, and it is now preparing to be launched from our launch facility. Which brings up a whole new interesting topic. Laddie is going to be the first lunar launch from NASA's Wallops Flight Facility. We're not launching from the Cape, we're launching from Wallops. It's been a long-established launch facility for sounding rockets, exploring the upper atmosphere. Recently, it's been putting stuff into Earth orbit, but this is the first time we're going further. We are also going to be the first payload to ever fly on the brand new Minotaur 5 rocket. Yahoo! You know, as if this wasn't exciting enough. So we're not going to take this quick 4-day trip to the moon that you may have been used to. We're actually going to take about a month to get there. In a series of phasing loops. Loops that get progressively higher and further away from the Earth and eventually be captured by the moon. It's a low energy transfer. Once we get there, we'll spend, again, about a month going through a checkout orbit, make sure everything's fine, and then we'll drop down into our science orbit. 100 days of science mission, flying through the lunar atmosphere, and at the end of that 100 days, we will be directed to impact into the far side of the moon.
Why the far side?
Because basically one of the things that we really want to do is make sure that we do not cause any damage to the heritage sites on the near side.
Won't this eventually become a heritage site?
No, in the case of, in our case, because we are going to impact, we would be kind of a heritage debris field. So a little more on the rocket we're going to be flying. Again, the first flight of the Minotaur 5. And the Minotaur 5 is really very interesting because its engines actually are recycled. They were reclaimed from the old Peacekeeper MX missile system that you may have heard about that was designed to destroy the world. And under treaty, these missiles were disassembled and they were to be dismantled and destroyed. Well, what better way to dispose of those engines than to use them to send things into outer space into the moon? So that's what Orbital has done here, and so we're really looking forward to taking advantage of this swords into plowshares story. Again, we're launching from Wallop's flight facility. There's an interesting story right there in and of itself, because Wallop's is very close to some of the major population centers of the United States. The East Coast is where most of the people live. We're close to DC, we're close to Baltimore. As a matter of fact, because we're scheduled to launch at night, if weather conditions are perfect, under ideal weather conditions, 60% of the population of the United States could be able to look out and see our launch. Sometime back, Wallops launched a Minotaur 1 rocket, a little brother to our rocket. Nighttime launch, and it was visible as far west as Detroit, Michigan. So we're looking forward to putting on a show. If you want to know about launch events, and there will be launch events, go to moon.nasa.gov and follow the Laddie launch link, and you can find out the latest on what's going to happen and how you can view it. But it isn't just something we want you to watch. We're looking forward to having people actually participate. This is a mission that there are a number of ways that students and the public can participate in. One of them, the Goldstone Apple Valley Radio Telescope Program, run by the Lewis Center for Education Research and JPL, is a great example. Through this, students across the country and around the world, from their classrooms, will be able to take remote control of some of the giant 34-meter dishes out at NASA's Goldstone facility. And students will be able to track and monitor the health and status of our spacecraft in flight. During the cruise phase, they may be listening at times that we are not. So if we were to go into safe mode, it's quite possible that a student might be the first to hear that. Once we get there, they'll be able to watch the firing of our engines, see how we change the orbit. We did something similar with the All-Cross mission. We had high school students listening to the Doppler shift in our carrier, and they were able to tell us what the delta V was when we fired our engines. Now, the Doppler shift has been demonstrated in classrooms for a very long time, but I gotta think this is one of the cooler ways of doing it. Amateur astronomers are uniquely positioned to be able to participate in this mission. As I mentioned, meteorite impacts are thought to be one of the major sources for the lunar atmosphere. And it turns out that the flashes of meteorite impacts on the lunar surface is visible from here on Earth. And it is best recorded using telescopes with apertures of 8 to 14 inches. That's a very common type of telescope for amateur astronomers in a lot of schools. So what we're hoping to do is have a network of observers around the world watching the moon during our mission, recording those impacts so that we can correlate changes that Laddie's instruments see in the structure and composition of the lunar atmosphere with these impact events, and thereby better understand the role of impacts as a source for the lunar atmosphere. This is an example. This is a video loop taken by an amateur with an 8-inch telescope. You can see the bright sunlit side of the moon up here, the earth-lit nighttime side of the moon down here, and if you look down in the lower right there, you'll see a flash. That's a meteorite impact. That's something about the size of a walnut striking the moon. These are the types of things we're looking for. Well, that's great if you happen to have an 8 to 14-inch telescope. Hands, how many of you do? That's a lot better than average. That's very good. And we want you. But there are a lot of people who don't and who still would like to participate, and they can. Because it turns out the typical impactor, the most common type of impactor hitting the moon, has a diameter of 1 micron. And we would never see that kind of a flash from here on Earth. But even a very small piece of debris can become very evident when it hits our atmosphere and lights up the sky as a meteor. The typical meteor that you see up in the sky is caused by a solid object about the size of a grain of sand. And because the Earth and Moon travel through space together, and they encounter these streams of debris together, if you go out and count meteors here on Earth, we can then make inferences as to what is happening on the surface of the moon. The beautiful thing about counting meteors is the equipment requirements are essentially nothing. You do not need a telescope, you do not need binoculars. I do recommend a reclining lawn chair. But as is the case with almost everything these days, there's even an app for that. So the ingeniously named Meteor Counter App, developed by NASA's Meteorite Environment Office, allows you to go out into the nighttime sky. Your smartphone knows where you are, it knows what time it is. You run the app, and you just start tapping on the screen as you see meteors. Tap on the left for a dim meteor, right for a bright meteor, in between for an in-between meteor. Your phone records that. At the end of your observing session, it uploads that data to NASA. Anyone can be part of our science team. This is a mission that anyone can participate in. If you are a radio enthusiast, an amateur radio enthusiast, there's a special opportunity for you here too. Because we can see meteors during the nighttime, but a number of showers approach us from the daytime side. And we'll never see those. But radio amateurs have long known that they can hear them. They can listen, they can hear signals reflecting off those ionized columns of gas. And so we can get additional information on meteor counts, including daytime information, if a meteor shower happens when it's cloudy, or if you're observing from a place that's overly lit, we can still get valuable information from the radio amateur community. So with that, I will entertain any questions with the understanding that you're going to be hearing a lot more about this today in a lot more detail. This is just kind of your introduction.
In your presentation, how many different ways did you list you want the public to participate?
So we had 4 different ways. Okay. So we have the Gabbard program, we have the Lunar Meteorite Impact Observation Campaign, we have Meteor Counting visually, and then we have amateur radio.
Thank you.
Mm-hmm. Anything else?
Is there any plan to work with CAMs on the meteor side of things?
We have talked a lot with Peter Yaniskas. He's just down the road, and he's here. Saw him yesterday. And so, absolutely, we will draw our information from a number of sources. So, there's the CAMS program. there is the American Meteor Society, and there's the International Meteor Organization. And so these are already gathering data. We're not creating new programs here. The Meteor Counter program existed before Laddie came along. But what we are doing is we're providing added value, perhaps motivation. The cachet of a moon mission may be a little more incentive to get up at 2 in the morning and go look at the sky. So we're just providing added value to these existing programs, and then the data that they get will be of value to us. So it's a win-win. Yes?
In what ways do you foresee using this data once it's collected?
Primarily, in terms of the impact observations and the meteoroid observations, the gentleman in that far corner back there is Rick Elphick, and he's our project scientist. And so he and his colleagues, as they're collecting this information from the instruments on Laddie, they will have a history because one of the things we're really looking at is the variability of the structure and composition of the lunar atmosphere and the distribution of dust, possibly. Again, big question mark. I'm going to answer that question from the Apollo days finally. But we'll see these variations over time. And so being able to provide them with a data set saying, here is a list of impact events that happened during that time of your observation, that will be a very interesting data set to correlate with the one that they have gotten from the Laddie instruments. So I am looking forward to hearing great things from them.
Thank you so
Thank you.
much, Brian.
Thank you.